Some of the same work that we've done on permutations, which are words that have no repeated letters, can also be done on rearrangements of arbitrary words that do have repeated letters. And a lot of the work we've done is going to come out almost the same on word rearrangements. So let's use this multiset terminology, multiset notation for words with repeated letters. So let's write 1 alpha 1, 2 to the alpha 2, etc. up to m to the alpha m to be the word that has alpha 1 1s, alpha 2 2s, etc. up to alpha m m's. And define capital R of 1 to the alpha 1 dot 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 m to the alpha m to be the set of rearrangements of that word. So this is kind of like the symmetric group is for permutations. So for example, let's look at the rearrangement set of the word 1 1 2 3. So there's 12 rearrangements of 1 1 2 3 because we've got 2 ways to choose where the ones are going to go, and then for every one there's 6. For every placement of 2 1s, we can have the 2 before the 3 or the 3 before the 2. So we have 1 1 2 3, 1 1 3 2, 1 in positions 1 and 3, 2 3 3 2, 1 in positions 1 and 4, 2 3 3 2, 1 in positions 2 and 3, 2 3 3 2, and 1 is in position, oh, we've got 2 more positions of 1s to go, 2 and 4 or 3 and 4. So we can define a descent in a word rearrangement just like we do in a permutation. It's a large letter followed immediately by a small letter. So let's mark in the descents. 3 is bigger than 2, 2 is bigger than 1, 3 is bigger than 1, 3 is bigger than 1, 3 is bigger than 2, which is bigger than 1, 2 is bigger than 1, 3 is bigger than 1, 2 1 3 1, 3 1 2 1, 3 is bigger than 1, 3 is bigger than 2, which is bigger than 1. So the number of descents is 0, 1, 1, 1, 1, 2, 1, 1, 2, 2, 1, 2. And then we can define the major index to be the sum of the descent positions, just like we would for permutations. So major index is going to be 0, 3, 2, 2, 3, 2 plus 3 is 5, 1, 1, 1 plus 3 is 4, 1 plus 3 is 4, 2, and 1 plus 2 is 3. We can define inversions just like we did for a permutation. So it's a large letter followed sometime later by a smaller letter. None there because the letters are all in order. 3 is bigger than 2, so that's 1 inversion. 2 1 is 1 inversion. 3 1 is 1 inversion. 2 1 and 3 1 make 2 inversions. 3 2 3 1 2 1 make 3 inversions. 2 1 2 1. So there's 2 different ones. We can get that inversion twice. Well, 2 different inversions. 2 in this one, 2 in that one. 3 in this one, 3 in that one, and then 3 and 2. So that's 3. 2 in this one, 2 in that one, 3 in that one. So that's 3. 3, 1, 3, 1, 3, 2. So that's 3 so far. And 2, 1 makes 4. 2, 1, 2, 1, 3, 1, 3, 1. That makes 4. And then 1, 2, 3, 4, 5 here. Now it turns out that, oh, I might have done this incorrectly because major index and inversions are supposed to be equally distributed. There's 2 inversions here, 3, 1 and 3, 2. I only counted one of them. Alright, now let's see if they line up. So we've got a single 0, 2 1s, 2 1s, 1, 2, 3 2s, 1, 2, 3 2s, 1, 2 3s, 1, 2 3s, 2 4s, 2 4s, single 5, single 5. Okay, that's good. Major index and inversions are equally distributed on the rearrangement class of any word. Although we can't prove that the same way we did, because if we look at all the major index tables and all the codes, it's not going to be the same set of words. So a different proof is needed to prove that. Now descents are also equally distributed with another statistic called exceedances. Although exceedances is the only one of these 4 statistics that needs a new definition, because the old definition of descents, major index, and inversions extended in a very straightforward way to word rearrangements. For exceedances, normally we'd be looking, is the first letter bigger than 1, is the second letter bigger than 2, is the third letter bigger than 3, is the fourth letter bigger than 4. But that's sort of not fair in a word that doesn't have any 4s. These letters are 1, 1, 2, and 3. So to compute exceedances, we're going to count every time that the ith letter is bigger than the ith letter in this weakly increasing word. So let's let W be a rearrangement of 1 to the alpha 1, etc., m to the alpha m. We'll call index I an exceedance of W if Wi is greater than the ith position of this word, 1 to the alpha I, m to the alpha m. So we'll be comparing each word here to the word 1, 1, 2, 3 in the example. So here 3 is bigger than 2, so that's 1 exceedance, and there's no exceedances in the word 1, 1, 2, 3 itself. 2 is bigger than 1, so it's 1 exceedance. 3 is bigger than 1, so it's 1 exceedance. 1 is the same as 1. 2 is bigger than 1, and 3 is bigger than 2, so that's 2 exceedances. 3 is bigger than 1, so it's 1 exceedance. 2 is bigger than 1, same, lower, same, just 1 exceedance. 3 is bigger than 1, same, lower, lower, just 1. 2 is bigger than 1, 1 is the same. 3 is bigger than 2, so it's 2 exceedances. 3 is bigger than 1, and that's it. 1 exceedance. 2 is bigger than 1, 3 is bigger than 1, so 2 exceedances there. 3 is bigger than 1, 2 is bigger than 1, so 2 exceedances there. Alright, now this should be equally distributed with descents. So we have a single zero, a single zero. 1, 2, 3, 4, 5, 6, 7 ones. 1, 2, 3, 4, 5, 6, 7 ones. 1, 2, 3, 4 twos. 1, 2, 3, 4 twos. Okay, so I did this example correctly. So the facts are that exceedances and descents are equally distributed on the rearrangements of any word. And inversions in major index are equally distributed on the rearrangements class of any word. And let me write down what I commented on. So we could define a major index table. And if we look at all the major index tables of W for W in the rearrangement class of any word, that set is not equal to the set of all codes of rearrangements of that same word. So that's not the outline of the proof. And it's also true, so we've got 3 facts here. Another fact that we probably won't need, but might as well know, that Dumont's code statistic, we could write codes for how many letters, the ith letter in the code would be how many things are to the right of and smaller than the ith letter in the word W. And then we can count the number of distinct letters in that. That happens to be equally distributed with descents. So maybe we can do a couple of those just for fun. So I've erased a few rearrangements, but we can just do it on the last 8 that are here. So we can make the code for every letter we count how many things are to the right and smaller. So this would be 0, 1, 1, 0. 0, 2 things to the right and smaller, 1 thing to the right and smaller. 2 things to the right and smaller, 0, 0, 0. 3 things to the right and smaller, 0, 0, 0. 2 things, 0, 1 thing, 0. 3 things, 0, 1 thing, 0. 2, 2, 0, 0. And finally, 3 things to the right, 2 things to the right and smaller, 0, 0. And the Dumont's code statistic would just be the number of distinct letters that we see here. 2, 3, 2, 2, 3, 3, 2, 3. And these are, so these numbers are 1 bigger than what we'd expect to see for descents. So the code statistic is always going to, we'll always have at least 1 letter that is 0. If we look at 1, 1, 2, 3 in order. And we'll have at most 3 different letters here in Dumont's code statistic. So it's going to be between 1 and 3, and the number of descents we can have is only 2, somewhere between 0 and 2. So the range of values is going to be different, but actual distribution is going to be the same. The end.